Sometime tomorrow morning, a piece of a rocket that has been lost in space for a year and a half is going to hit the moon and dig a brand new crater into a world that has kept its scars for 4 billion years.
No one planned it, no one can stop it, and a small army of astronomers have set their alarms to watch.
A good day, and welcome to Astronomy Daily. I'm Anna.
And I'm Avery. Today is all about impacts, the ones we make and the ones the universe made long before us.
A dead Falcon 9 about to punch the moon, the asteroid that may have charbroiled the dinosaurs within hours, the ancient smash-up that shattered Neptune's moons, and then, to zoom right out, a new map that just doubled the X-ray sky.
Plus a both-hemisphere skywatch with a genuinely special comet in it. Let's get into it.
So let's start with the story everyone will be talking about tomorrow. Early on Wednesday, the 5th of August, at about 6:35 Universal Time, a spent upper stage of a SpaceX Falcon 9 is going to slam into the far western edge of the moon's near side, close to a feature called Einstein Crater.
And this isn't a controlled landing gone wrong. This is a genuinely derelict object, space junk, finally running out of road.
Exactly. Let's rewind. Back in January 2025, a Falcon 9 launched from Kennedy Space Center carrying 2 moon-bound landers, Firefly's Blee Ghost, which went on to land beautifully, and iSpace's Resilience, which sadly didn't survive its own touchdown. The landers separated and went on their way, but the rocket's upper stage, the big second stage tube that does the final push, was left stranded.
Too high to fall straight back to Earth, too slow to escape cleanly. So it just wandered.
For about 18 months in a long, chaotic loop shaped by the tug of the Earth, the Moon, the Sun, and even the faint pressure of sunlight itself. It's cataloged, unglamorously, as 2025-010D, and an independent astronomer named Bill Gray, who runs the tracking project Project Pluto, has been following it the whole way.
This is the same Bill Gray who called the last one, isn't it?
It is. A few years back, he identified another derelict stage on a lunar collision course. This is his second, and around March, watching the numbers tighten, he realized this one wasn't going to be a near miss. It was going to connect.
So give us the ballistics. How hard does a thing like this hit?
It's roughly a 4-ton object, about a 12-meter metal tube arriving at something like 2.5 kilometers a second. That's about 5,500 miles an hour, comfortably faster than a rifle bullet. The energy release is on the order of 3 tons of TNT.
And what does that carve out?
Best estimates put the new crater somewhere between about 17 and 27 meters across and a few meters deep. Small on a lunar scale, but here's the thing that has scientists genuinely excited. We will know almost to the second and to within a few kilometers exactly when and where a known object of known mass and known speed hit. That's an extraordinarily rare natural experiment.
Because normally a fresh moon crater just appears and you're working backwards.
Right. Here we get to work forwards. NASA's Lunar Reconnaissance Orbiter can photograph the site before and after, and because Bill Gray can hand the orbiter team a pinpoint, they'll know precisely where to look for the new scar. That before and after pair is gold for understanding how craters actually form and how the lunar surface throws material around.
And there's a whole observing campaign around it too, I gather.
There is a paper with something like 24 authors is coordinating professional and amateur observers to try and catch the ejecta plume, the spray of debris thrown up at the moment of impact. Now, I want to be careful here because this feeds straight into our skywatch later. You are not going to see a flash with your eyes. The impact is on sunlit ground near the day-night line on the moon's western limb. The plume is a long shot, even for advanced amateurs with serious instruments.
But timing-wise, who's best placed?
America's, north and south. For North American listeners, it's about 2:35 in the morning Eastern, pre-dawn, moon well up in the west. We'll give Southern Hemisphere viewers the honest picture in the Skywatch, because from here in Sydney, the moon is actually below the horizon at impact.
Anna, can we talk about the uncomfortable part of this? Because a rocket hitting the moon by accident is a great story, but it's also a warning, isn't it?
It really is, and I'm glad you raised it. This is only the second time we've ever documented an uncontrolled rocket body hitting the moon. The first left a pair of craters on the far side back in 2022, two in a few years. And as commercial lunar traffic ramps up toward permanent moon base plans later this decade, the amount of hardware drifting around in cislunar space, the region between Earth and the moon, is only going up.
And unlike low Earth orbit, there's really no rulebook out there.
That's the crux. In low Earth orbit, we at least have debris coordination guidelines. For cislunar space, there is no equivalent international framework, no agreed way to track, catalog, or safely dispose of these stages. Longtime listeners will remember we covered a study just last week on debris in distant retrograde orbits around the moon and how it becomes a hazard as traffic grows. This impact is that abstract worry made suddenly, literally concrete.
Interestingly, the industry does seem to be learning. I read that a more recent SpaceX upper stage was deliberately parked in a long-term solar orbit rather than left to wander.
That's right. A commercial choice, though, not a regulation, which is rather the point. So tomorrow morning, when a lost rocket finally comes home to the moon, it's worth holding two thoughts at once. It's a rare and valuable science opportunity, and it's a small, bright flag planted on a problem we haven't solved yet.
One crater, two lessons. Beautifully put. Speaking of ancient scars, shall we go and look at some far older wreckage?
Let's. Over to you.
Go out to the cold edge of the solar system, to Neptune, and you find a little family of small inner moons huddled just outside the planet's rings. Voyager 2 spotted most of them on its one and only flyby back in 1989, and ever since they've been too small and too far to really study, until the James Webb Space Telescope turned its spectrograph on them.
And this is a Caltech team, Mike Brown's group, the Pluto killer himself, led by Riley Davis.
The very same, and what they found genuinely startled them. In the light from three of those moons, Larissa, Galatea, and Proteus, and in the rings, they detected clay minerals, specifically magnesium-rich phyllosilicates.
Play in the outer solar system. Why is that such a shock?
Because phyllosilicates had never been seen anywhere out there beyond Jupiter, and crucially, clays only form in the presence of liquid water. As Davis put it, it was simply not on their list of things to look for. It hit them in the face. You don't make these minerals on a tiny, cold moonlet. You make them deep inside a much larger world with liquid water in its guts.
Though the material is telling you it came from somewhere bigger, somewhere that no longer exists.
That's the whole story in one sentence. The leading explanation is dramatic. Neptune once had its own orderly system of moons, much like Uranus does today. And then Triton arrived.
Triton being Neptune's giant, backwards orbiting moon.
Right. And the smoking gun is that backwards orbit. Triton almost certainly didn't form at Neptune. It's a captured Kuiper Belt object, a big icy world that wandered in from further out and got gravitationally snared. And the process of capturing something that large would have been catastrophic for whatever moons were already there. It would have scattered and shattered the original family.
And these little inner moons
are the reassembled shrapnel, rubble from the interiors of those destroyed worlds, exposed by the smash-up, some of it drifting back together into the moonlets we see now. Davis called it seeing the fingerprints left behind by that process. There's even a neat consistency check. The largest of the three, Proteus, doesn't show the clays. And the team think it's because it's big enough to have reheated and reprocessed itself after reforming, hiding its past better than its smaller siblings.
That's a lovely detail. The biggest one is the best at covering its tracks. And it ties us right back to the top of the show, doesn't it? A crater tomorrow, a demolished moon system billions of years ago, same violence, wildly different scale.
The solar system builds by breaking things. And it means the next spacecraft we send out there, and an ice giant mission is a top priority whenever it happens, would be flying to a genuine crime scene.
Down to the most famous impact of them all, and a new twist on how it actually did its killing. 66 million years ago, a roughly 10-kilometer asteroid struck what's now the Yucatan Peninsula, and the age of the dinosaurs ended. The long-standing picture is a slow death. Dust and soot blot out the sun, an impact winter sets in, food webs collapse over months and years.
The years of darkness story, which is grim but slow.
Right. But this new study out of Purdue, Brandon Johnson and colleagues in the Journal of Geophysical Research, argues the very first few hours may have been far more brutal than we thought. Their headline essentially is that exposed animals could have been charbroiled within hours.
Charbroiled being the technical term.
Near enough. Here's the mechanism. The impact vaporized an enormous amount of rock and flung it skyward. Some of that cooled into tiny glassy beads, spherules, which rained back down, and the friction of all that debris re-entering the atmosphere creates a global heat pulse. That part we knew, but earlier models suggested the heat pulse, while nasty, might not be enough to set the whole planet alight.
So what did this team add?
Dust, not the beads, the ultra-fine stuff. A huge quantity of rock vapor never condensed into spherules. It stayed as microscopic dust high in the atmosphere. And when they put that dust layer into their simulations, it acted like an insulating blanket, trapping the heat from all those falling particles and radiating it down. Their number is striking, surface heating about 3.5 times more intense than the beads alone.
Enough,
they argue, to ignite spontaneous wildfires around the world and kill exposed, thin-skinned animals within the first hour or two. Johnson's line was that you're essentially in the realm of killing off almost everything in that first window.
So who survived that?
Exactly the ones you'd guess. Anything sheltering underground or underwater had a fighting chance, which starts to explain the winners and losers pattern of that extinction. And then, this is the elegant part. The same dust that cooked the surface in hour 1 goes on to block sunlight for years afterward. So it doesn't replace the impact winter idea, it bolts a ferocious opening act onto the front of it.
I do want to flag the honest caveat, though.
Please, and it's an important one. The clearest physical evidence for these global wildfires so far is really only found in North American rocks. A researcher not involved in the study, Alfio Chiarenza at University College London, made the fair point that we may eventually find a truly global fire record, but we just don't have it yet. So a compelling model, strong regional evidence, and a genuinely open question about how planet-wide those first-hour fires really were.
And the through line to today's show writes itself. The same basic physics that'll carve a modest hole in the moon tomorrow, scaled up, is what reset life on Earth. Okay, moving on. Let's pull all the way back now, from one new crater to nearly 2 million cosmic objects. The eROSITA X-ray telescope on the Spectrum Röntgen Gamma mission has just put out its second big public data release, DR2, and it is a genuine landmark for the high-energy sky.
X-rays meaning the violent universe, the hot stuff.
The hot, the violent, the extreme, growing black holes, exploded stars, million-degree gas between galaxies. eROSITA scans the entire sky every 6 months, and this release stacks the first 3 of those all-sky scans together. The result, around 1.9 million point-like sources, things like stars and supermassive black holes, plus about 64,000 extended sources, which are things like galaxy clusters and supernova remnants.
Put that number in perspective for me.
Happily. The previous Great All-Sky X-ray Survey was ROSAT back in the early 1990s. It cataloged around 130,000 sources, and that was the field's benchmark for 30 years. eROSITA's first release already blew past it. DR2 roughly doubles that again. As the lead author, Miriam Ramos-Ceja at the Max Planck Institute put it, every extra scan drags fainter sources up out of the noise.
And there's a specific old mystery this cracks, isn't there?
There is, and I love this one. For about 30 decades, we've known the flat disk of our own galaxy glows faintly in X-rays, the galactic ridge X-ray emission, without being able to prove source by source what's producing it. DR2 delivers the first direct census of a population of cataclysmic variables, close binary stars where a dense white dwarf is pulling material off a companion. And it turns out there are enough of them to account for that mysterious glow, a 30-year puzzle resolved by sheer completeness.
Though it's not one headline discovery, it's a map good enough to answer questions we couldn't even properly ask before.
That's exactly it. And it lands alongside a huge Sloan Digital Sky Survey data release. So a couple of 100,000 of these X-ray sources now have optical fingerprints and distances, which lets astronomers map growing black holes in 3 dimensions across cosmic time. It's infrastructure for a decade of discovery.
From a single rooftop-sized crater to a 3-dimensional map of the hot universe. Not a bad range for one episode.
Let's move on to today's Skywatch, both hemispheres.
Right, let's take all this upward and outward and bring it to your own sky. And we start, of course, with tomorrow's morning's impact.
The honest expectations version.
The honest version. To be clear, this is not a naked eye event. There's no flash to see. If you're a serious amateur in the Americas with a large telescope and a lot of patience, the ejecta plume is a long-shot target near the moon's western limb around 6:35 Universal Time. That's about 2:35 Eastern for North America, moon high in the west. For everyone else, the real payoff comes later, when the Lunar Reconnaissance Orbiter returns before and after images of the fresh crater. And from here, in the southern hemisphere, in Sydney, the moon is below the horizon at impact time, so this one's an after-the-fact story for us. Watch for those orbiter images.
Now, the one I'm genuinely excited about, the comet.
Comet 10P Tempel 2. It rounded the sun on the 2nd of August and made its closest pass by Earth on the 3rd, about 0.41 astronomical units, roughly 62 million kilometers. So right now, it's near its best, around 8th to 9th magnitude. That's not naked eye. Think large binoculars or a small telescope from a dark site, a small fuzzy patch near the globular cluster M30 in Capricornus. But here's why it matters. This is expected to be Tempel 2's finest return for the rest of the century.
And this one actually favors us in the south.
It does. A nice one for our southern hemisphere listeners, where the comet climbs higher and sits up for much of the night. Northern hemisphere friends, you can catch it too, but it stays low over your southern horizon, so you'll want a clear, flat sky in that direction. Your darkest window opens on the nights around the 7th and 8th once the waning moon is out of the way.
Anything for the early evening crowd who don't fancy a midnight comet hunt?
Yes, look west after sunset tonight, and you'll find brilliant Venus threaded neatly between 2 bright stars, Regulus, the heart of Leo, and Spica in Virgo. A lovely, easy lineup for both hemispheres, no equipment needed. And if you're an early riser, Mercury reached its best morning showing on the 2nd and is still hanging low in the pre-dawn east. Catch it before the twilight drowns it out.
And then the big one. Mark the calendar.
The 12th of August, an enormous day. A total solar eclipse sweeps across Greenland, Iceland, and Spain, Earth's first totality in more than 2 years. And on the very same day, the Perseid meteor shower peaks under a new moon sky, which is about as good as the Perseids ever get, plus a 6-planet alignment. We'll build up to all of it over the coming episodes. And the essential safety note, which we will repeat every single time, a total solar eclipse is only safe to watch with your unaided eyes during the brief moments of totality itself. Any other time, and everywhere outside the narrow path of totality, you must use certified ISO 12312-2 eclipse glasses or a proper solar filter. Ordinary sunglasses will not protect your eyes. Please look after them.
Couldn't agree more. A spectacular sky ahead, watched safely. And that's our lot for today. Impacts large, small, ancient, and brand new.
If today's show sparked something, come and find us at astronomydaily.io. You can stream every back episode, follow our continually updating space news feed, leave us a review, drop us a note, and sign up for the daily newsletter so the cosmos lands in your inbox each morning.
Find us on social as @AstroDailyPod and tell a stargazing friend. Word of mouth is how this little show grows.
We are back tomorrow, and if you're in the Americas with a big scope and an early alarm, best of luck chasing that plume. Until then, from Anna
And Avery,
clear skies.